Assalamualaikum and hi everyone. This is pre-recorded video 19 for chemical bonding. In the previous video, we have learned a lot about hybrid orbital theory. There are 4 videos about hybrid orbital theory, and by now I hope you guys already master it. The last theory in theory of chemical bonding is MOT or molecular orbital theory. Similarly to VBT, this MOT also the foundational theory of quantum chemistry. I can say that all theories of chemical bonding complement each other. Not everything can be explained by VBT or VSEPR or HOT, so comes this MOT to solve the problems. However, there are some drawbacks of MOT. Well, the first one is it incorrectly assumes that electrons are localized, and so the concept of resonance must be added. Second, the model doesn't deal effectively with molecules containing unpaired electrons. And lastly, the model gives no direct information about bonding energies. This is a chemical structure of oxygen or O2 gas, no unpaired electron, and it should be diamagnetic. However, experiment shows that oxygen is paramagnetic. MOT can be used to explain that situation. A bit about the definition of MOT is a theory of the electronic structure of molecules in terms of molecular orbitals, which may spread over several atoms or the entire molecule. It includes orbital mixing, which is a combination of atomic orbitals forming molecular orbitals. You will see it in the next slide. And then in order for these orbitals to mix, they must have a similar energy levels and they have to overlap well, which is similar orientation, and be close together. This table shows the difference between MOT and VBT. For example, for VBT, a molecule is a group of atoms bound together through localized overlap of valence shell atomic orbitals. Okay, that's for VBT. However, for MOT, a molecule is a collection of nuclei with the electron orbital delocalized over the entire molecule. Okay, VBT is only on the valence part. MOT over the entire molecule. The second difference is each atom in a molecule retains its atomic orbital in a molecule. That's for VBT. For MOT, mixing of atomic orbital forming molecular orbital with a given energy and shape that are occupied by the molecule's electrons. Okay, you have to understand the meaning of atomic orbital and molecular orbital here. There are some conditions that we have to follow for MOT. These are the conditions and regulations of how the MO is arranged or configured. First, the number of molecular orbitals formed is always equal to the number of atomic orbitals combined. Second, the more stable the bonding MO, the less stable the corresponding anti-bonding MO. Okay, there are bonding and anti-bonding. The third one, the filling of MOs proceeds from low to high energies. Okay, this is quite normal, all right? Fourth, each MO can accommodate up to 2 electrons. Okay, this is same with Hans rule. Okay, fifth, use Hans rule when adding electrons to MOs of the same energy. Six, the number of electrons in the MOs is equal to the sum of all electrons on the bonding atoms. MOT is applicable for diatomic molecule, for example, H2 or hydrogen here. So two atoms H with one s and one s orbital can have bonding MO, which is enhanced regions of electron density, and anti-bonding MO. You can see the difference in the shape of orbital for bonding here. Okay, I'll show you. Okay, this is a bonding orbital and anti-bonding orbital here, which is the nodal plane. Okay, the energy for anti-bonding is much higher than bonding. AO is atomic orbital while MO is molecular orbital. Okay, we clear on that. Let's say we have energy level of 1s. In MOT, there is sigma 1s bonding and sigma 1s anti-bonding, or we put it as asterisk here. Okay, so this is shows the anti-bonding. The same principle applies for other energy levels. Okay, so 1s, 2s, AO, MO. The electron from each atom is being shared to form a covalent bond. This is an example of orbital mixing for H2 and H2 plus. H2 on the left and then H2 plus on the right. H2 has 2 electrons while H2 plus has 1 electron in the molecular orbital bonding and anti-bonding. You can see the difference. Take another example of diatomic molecule Li2. The yellow box are for atomic orbital and the orange box are for MO. We know that the electronic configuration for Li is 1s2 to s1. That one is for Li. In this case is Li2. So it should be double the Li. So the arrangements in MO, which is in the orange box, should look like this. It should start from the bottom, which is the lowest energy. So 3 electrons from here and 3 electrons from here, which is the atomic orbital. And this is molecular orbital. So the arrangements for electron is 1, 2, 3, 4, 5, and 6. This slide shows the shape of orbital for 2p electrons for bonding and anti-bonding. Basically for bonding, the clouds of electrons combine and getting bigger. However, for anti-bonding, the clouds are separated into 2 entities but connected. This is the energy level diagram for more orbitals from lower to higher energy. This one includes the bonding and anti-bonding levels for 2p orbitals. Okay, so let's say for 2s, you got sigma 2s here and sigma star 2s, which is anti-bonding for star. Okay, so for 2p, it got sigma 2p and then pi 2p. Okay, we know that there is one for sigma and then 2 for pi. And then this 3 belongs to sigma and pi for anti-bonding. This is a molecular orbital for F2, diatomic molecule F2. So on the left here, you can see the energy level diagram for F2. And then on the right here, you can see valence electronic configuration is different with the normal one that we've learned before. Okay, it started with sigma 2s and then 2 electrons in there, sigma 2s star and then 2 electrons in there, sigma 2p, 2 electrons in there, pi 2p, 4 electrons, 2 in there. Okay, 4 meaning that there are 4 electrons in there, and then 4 pi 2p star, which is anti-bonding, and also 4 electrons in there. So this is actually anti-bonding. You have to remember the energy diagram, this energy diagram. This is how we write the electronic configuration for MOT. However, the sequence is a bit different for group 1 to 5A, which is here, the first one. okay, the first one, and group from 6 to 8A, you have to follow the sequence of the energy level here, okay. And then the number of electrons is written as superscript. For example, we have B2 or boron 2 here. The total electron is 10. So you have to write sigma 1s to sigma 1s star to sigma 2s to sigma 2s star 2. Okay, so the superscript here are all the number of electrons occupied in that molecular orbital. And then pi to py1, there is only one electron, pi to pz1. Okay, so altogether 10 electrons. And then the sigma 1s and sigma 1s star are generally not shown, always written as kk. Thus the configuration of for B2 you can write as kk, and then you start with sigma to s and so on. Before we end this video, please do this exercise and discuss the answer with your lecturer. We continue MOT in the next video. Thank you.